Now let me show you a specific realization example of the architecture I just showed you. This is an example that we implemented a few years ago with Professor Dimitri Peroulis. He was a research scientist in our group at the time. He's now a professor at the University of Colorado. And the coupling diagram is actually right here. This is a coupling diagram that we improved upon a filter that was published actually by the Naval Research Lab, NRL. The original paper is actually shown right here. Our improvement is actually shown right here. But there are lots and lots of details to worry about. What I really mostly want you to see is how similar this thing is to what we have been talking about. And we're talking about the state-of-the-art design here. So look at, again, this is the source, this is the load. We are basically hanging resonators. These are all the resonators here. And we are basically creating a dual reflection again. So here's the first reflection, here's the second reflection. So we are talking about a passband filter approach. Now, each one of these resonators represents a different frequency. So here's F1, here's F2, here's Fn. That should give you the hint that we're talking about different bands, F1, F2, Fn. And to make sure that we don't have just a single order, basically a first order band, we repeat basically the same architecture multiple times. So for example, if you make two of them, you will end up with a dual, a two-pole response in F1, two-pole response in F2, two-pole response in F3, and so on and so forth. The great approach that Dimitri was able to investigate here is because of this architecture, you can essentially control each band separately. For example, I can change the resonant frequency of these guys only and keep the resonant frequency of the red resonator. And that means I can tune now the blue band, but keep the red band constant. Also, if you make these couplings here tunable, and I'll show you an example of how she was able to do that, you can essentially totally disconnect a resonator from the rest of the filter structure without basically impacting the rest of the response. So for example, you might be willing to kill the band F2 completely and make this guy totally disappear simply by killing the sections. So not only we have a totally independent bandpass control, so again, that means you can tune this band and the other one can be constant, but you can also decide how many bands you want to keep. So this is a very interesting design that gives you independent control in frequency and bandwidth of all bandpass, of all passbands, which is very, very difficult to achieve in general in a multi-band response. So it's really, this is the power of the technique that we're teaching here that I would like you to appreciate. And let me give you now a specific layout so you can see how we make these things in real life. There are many different details in this layout, so I don't want us to basically go in excruciating detail. But here's a few things I want you to look at. So first of all, here's the input, here's the output, right? So here's the source, here's the load. And we are basically having just two bands. So we're going to essentially make two resonators. So here's the first microstrip resonator that you will see right here. It's basically a microstrip line. The reason it's bent a little bit is because we're trying to save some space. And this is basically the same microstrip line again. And this is the same microstrip line again. So this is basically the same resonator in 3 copies doing essentially a third order response for that band. Now here's the other band here. So 1, 2, 3 resonators basically controlling the second band. And each one of these resonators is loaded with capacitances. So there are some capacitances right here. So here's one, here's another for the blue band. And these are basically the capacitances that will control the resonant frequency of this resonator. It's basically a transmission line that is loaded by the varactor, right? So, and as we have learned, when you take a transmission line and you load it with a varactor, you will basically get a different frequency response. So this CR1 this CR1 in all 3 cases controls the resonance frequency. Now on top of that, there are essentially coupling sections that are controlled by these varactors here. So you can see that this blue resonator here has to somehow be connected to the non-resonating node. And here's, by the way, the non-resonating node. It's just a connection point. And because we want a tunable coupling, instead of just connecting it through a static capacitance, we can basically connect it through this one. Remember that we talked about, for example, inverters that looked like this, right? or inverters that had basically negative transmission line sections. So, and these negative transmission line sections could have been absorbed in the main resonator, and this is exactly what's happening here. So similarly, the red resonator has its own tunable coupling, and again, the same scheme repeats basically everywhere. So you can see essentially a one-to-one mapping between the coupling diagram that we're discussing here to a layout, and that is not as explicit always as I'm making it sound here, because the structure here is very simple. It's a microstrip implementation, so you can clearly see it, and that's why I'm presenting it. But even if you can't see it as explicitly, this is always how it's done once you choose the fabrication technology, which we'll discuss in a little bit. So let me show you some examples. This is essentially the measured response. I want you to notice a few things here that are coming from the non-ideal realization. So first of all, you should all be careful about this part here, which is the insertion loss, right? So we're talking about the microstrip transmission line. As you have listened to the recorded lecture, this has a finite Q. The Q is usually in the order of 80, maybe 100, somewhere there. So there is a respectable insertion loss, which you expect because of the chosen technology. You can also see that the bands can be tunable. So here's an example where you can tune both bands. Or, as I mentioned before, you can have independent tuning control. For example, in this case, this band here is kept constant, while the second band is being changed by essentially changing the capacitances. And this third graph here is showing what I promised before, that you can basically make a band appear or disappear. So for example, this band here, it may be completely killed simply by killing the coupling sections that control that. So again, you can read the paper if you want to look at more details, but here I just mostly want to focus on mapping what we are learning to a physical realization.